Yeah, hi. This is my third video, and now I am going to show you how we can use an expression of the electric field to calculate the electric potential. One thing that I want to say before I start that when electric field and electric potential of a conducting sphere, when electric field and electric potential of conducting sphere are calculated, or like we have these expressions, the expressions can be used for for a conducting shell, okay? For a conducting shell. Now, what does that mean? What's the sphere? The sphere, it is when you have all this material filled in. Okay, when it is shell, it's just the outer sphere, like, like it's like a volleyball or a basketball. Then the expressions for both are the same. And the reason is that because it is conducting, okay, then the sphere charge will accumulate on the outer surface. Then it's gonna be like similar to the shell. No charge will be inside the sphere. Okay, now, let's assume here we're gonna calculate now for the sphere. And again, there is a way to calculate when it is inside and when it is outside. Then here, my point P is outside P, and this is my R, all right, and this is Q. It has a charge of Q. Now we can say that V at any point R minus V at infinity should equal the expression minus, okay, from infinity to the point E dot dr. We know that this was derived in chapter, I cannot remember, either by integration by the end of chapter 21 or using Gauss's law. Like we can either one, but it's the same expression. I mean, this is actually the electric field of a sphere. Now I can say also that then I can substitute this for the expression for E, 1 over 4 pi epsilon 0 Q over R squared unit vector R times dr. Now what I can do also here is all my constants, I can pull them out. Then Q over 4 pi epsilon 0 are pulled out. And here I have R unit vector, which is going to be 1 times dr times cosine 0, which is 1, divided by R squared. And that will result in minus Q over 4 pi epsilon 0, again infinity to R, and this is going to be dr over R squared. Now let's integrate. Okay, then minus q over 4 pi epsilon 0. The integration, it is negative 1 over r. And what I can do is I can write it this way. I'm doing it like in more details. Okay, negative 1 over r from infinity to r. And finally, this is going to be a plus because negative 1 over r minus 1 over infinity. And here, of course, we know that this is VR minus V infinity. By definition, this is 0, and therefore my VR is going to be a plus Q divided by 4 epsilon 0 R. And it is, of course, very, I will not say it is very, it is the same expression as the one for point charge. Okay, because, okay, again, looking from outside, it's very similar to, let's say, focus that this is going to be, I will say, the charge accumulating at the center, or it is actually, okay, very similar to the point charge that we're talking about. Now next, let's move to another way of, okay, like the second one. Now, when the point is inside the sphere, all right, then here inside the sphere, I will say I need to do again the integration, and this is my sphere. It has a radius r. My point is somewhere inside in here. All right, this is my point P, and then here I will say V of r minus V of infinity should be again minus from infinity to r again, E dot dr. Remember, I did say that anytime I will have I'm gonna have two regions, then I need to consider the changes. Then in my way from infinity to r here, I am moving from outside the sphere to inside the sphere, right? Then I need to consider here dissecting my integration from infinity to r, which is outside the sphere, and r to 0 inside the sphere. And again, V of r minus V infinity is minus from infinity r E dot dr, and that equals minus from infinity to uppercase R E dot dr minus from R to 0 E dot dr. Now we know that the second expression gives 0 because E is 0 inside the sphere. Therefore, I will say now I am left over with the first term, which is infinity to r E dot dr. I'm going to use the expression very similar to what I did in my first step. R unit vector dr. And then finally, I'm going to have it q 4 pi epsilon 0 from infinity to r of 1 over r. And therefore, this is the expression. And it is a constant value, right? Then it is, if your point, it is inside the sphere or it is on the surface of the sphere, all the points, they have the same potential. And that is what is, we call it equipotential surface. Then like it is all the points, they have the same potential. Which means if I will calculate it, put in this r equal the magnitude of the radius, then this is the potential for every single point inside the sphere. Thank you, and I'll see you in another recording soon. Thank you.